who is currently a postdoc at MIT. You guys have seen her a bunch. She'll be joining UIUC in the summer. And she will be talking to us about Dr. Seuss.
Thank you. I'm going to talk with, this is joint work with Manish Raghavan called 1AI, 2AI, Red AI, Blue AI is the fun talk title. So I'm going to start out with a motivating example. Suppose hypothetically that you're a user and you have some task that you want help with. Let's say that this task is making a plot. And you can do this yourself, but you want to see if a model could help you. So you pull open a model and it gives you a response that is some value. So for right now, let's assume values are between 0 and 10. So a value of something 5 is like helpful but not perfect. And so you're like, can we do better than this? Maybe other models will help or will give different or better answers. And you ask your other favorite models, and they all give you different answers, and some of them are better, and some of them are worse. So as a user, you get some utility for a set of models. So let's say you're doing something like aggregating across the set of models. I'll get much more specific about this in a few slides, but for right now, just think of this as taking some sort of noisy aggregation, like noisily picking the best response from a set of models. So you don't have one task you're interested in. You maybe have many tasks that over your sort of lifetime you're interested in solving. One of them could be write a poem, for example. And you might similarly ask a set of models and get a different set of responses. And models might differ systematically in their strengths. So some of them are better at making plots. Some of them are better at writing poems. And similarly, you get utility from aggregating across multiple different models. So at a high level, let's zoom out and see what's happening. So the consumer has utility by imperfect aggregation over a set of models that have different strengths and weaknesses. And this could be model consumer choice. That's a running example and we're working throughout this. You could also view this as routing. So you have some router here that's just sort of acting as the user, and they're trying to get higher utility by picking the right model for a query they're looking at. So this is the high-level thing that we're going to be talking about. So there are two questions you might be thinking about if you're in this setting, if you're this user. One question might be, what market of models is best for me? So I have this set of this hypothetical market of models. Is this a good market? Is this a bad market? And the second question you might be interested in is, how can I incentivize firms to make a market of models that's good for me? So what's good for me, and how can I make firms make this? So those are the two questions we're going to be talking about for the rest of this talk. And I'm going to spend a little time focusing on imperfect aggregation and being a lot more specific about what I mean in this particular setting. As a warm-up, let's talk about perfect aggregation. So what does it mean in this setting to have perfect aggregation? Looking at this particular set of examples, there's sort of different values in different models. We're going to define perfect aggregation as always picking the right model for any task you're interested in. So it would look like this. You'd always get value 9 for both of these because there exists a model with value 9 on each of these tasks. And notably, requiring perfect assumption or perfect aggregation requires that this is true no matter what the other values are. So no matter whether they're very bad or very close to perfect, you would still get the best one. And this would also be true no matter how many models there are in the market. So even if there's like many, many models, you're always going to find the best one. On the opposite extreme, you could also consider random aggregation, which is just sort of saying you randomly pick a model. You don't really care whether it's better or worse for your task. We're going to view these as two extremes. We're going to look at something that's in between. So in particular, we're going to think about, yes, this is random aggregation, just taking average. We're going to look at something that's better than random, but worse than perfect, and see how this sort of affects user utility and incentives we're interested in. And in particular, we're going to model the user's utility as given by a choice function. So the utility is basically the value of each response from different LLMs multiplied by the probability of finding that. So what does the two extremes look like here? So perfect is just probability 1 on our single best answer. Random is uniform flat probability. We're going to look at Bradley-Terry-Luce, softmax, whatever you want to call it, something like this, which has a tunable noise parameter. On one extreme, it looks like perfect aggregation. On the other extreme, it looks like random aggregation, and we're going to play with changing this noise parameter. And so the purple bars represent different noise parameters, basically more or less accurate. And temperature will be an important factor we talk about later. Yes?
Just a clarification about the perfect setting. So in the perfect setting, you're assuming like the model with the maximum value is picked.
Yes.
But then could it be that, like, so for example, here value equal to 9 for the best, but then maybe that 1 point that is missing on a scale of 1 to 10, that comes from another model?
Yeah, so great question. We're not allowing people to combine responses across models. That would be a really great extension. But here you're just saying it's sort of a choice function, so you're picking some response out of the set that's given. Does that answer your question?
Yeah, so but then how is it aggregation?
That's a great question. You could view this as choice. I guess if you're aggregating across a set of responses, but that's a fair point. We could have called it many other things. Yeah.
Got it. Thank you.
Any other questions currently? Yes.
So do we have to have the actual quantifiable valuation, or is it just some pairwise preference? That's
Great
all.
question. I will get to this later. So basically, the TLDR for later is that in order to make better mechanisms, you are going to need the values. Pairwise is not going to be strong enough to get what you want, but great question. Cool. So now I'm going to get into the model in slightly more detail. So we have different tasks. We have different models with different values across tasks, and user utility is given by aggregation or choice function across multiple models. Two main questions I'm going to be interested in, the two sort of halves of this talk. The first is what set of models is best for user welfare? So basically, what does a healthy marketplace look like in this setting? And the second is how can we incentivize model creators to produce such models? And two things we're going to be interested in, so really important things, are the model creator actions. So if I'm a company, what actions can I take in this setting? And there are two different types of actions we're going to be looking at. So one is create new models from scratch, and the other is fine-tune or replace existing models. So I'll just have a cute diagram showing what happens. So creating new models looks like this. There are two models in the marketplace, and then a new model enters. One important thing, we're going to hold total value on tasks fixed. So you can't say, great, I'm making a new model, it's perfect in every task. There's some total max value that you have to allocate across tasks. So happy to talk about that more as well. The other thing, replace existing models, looks something like this. So here we have one model with values across two tasks. And then I've just replaced it with slightly different values across both tasks. So you should view the replacing, we're thinking, as more of a fine-tuning. So it's a small local change in relative strengths. The creating new models is like a big action that you can sort of completely reallocate values as you choose. Yes?
I'm trying to wrap my head around the full model here.
Yeah.
And I understand you have GPT, Claude, and Gemini up there, but
Yeah.
it seems like one action for a creator would be aggregation. So would that, I guess I'm trying to think through how that would change the game. Oh, sorry, yeah.
I can read it.
Sorry, so one action for the creator might be aggregation, and so I'm wondering how that might change the game. In principle, it might just be another perturbation to the model, but then I guess I'm wondering if that interacts with user utility, you might be able to get different results than you would in the model you have.
So you could say, for example, I'm going to create a new model. This model is just going to sit on top of other models and query all of them.
Which is literally, right, that's what
Yeah, so that's a great question.
model aggregators do, yeah.
That is a great question. That's not something we allow in these two actions. That would change this, and that would sort of break our assumption here that the total value is fixed,
Yeah,
because then you could aggregate. That would be super cool, and I assume if you allow people to do that, then you would just always choose to do that. Crucially, you'd have to be sort of accurate enough. So if you're aggregating and you're substantially worse than maybe the user is, this would probably not be helpful. But if you're sufficiently good at aggregating, this could be a great action. Yeah,
Okay.
Thanks for the question. Yes?
Is the total value fixed the same for all of the any new model then?
Great question. They can differ, and that is something we look at. So we're saying and ask questions like, suppose you're entering a market and you have value that's lower than the average value of the market, or like you're a powerful model or a weak model, and the results do differ based on that. Great question. Other questions currently? Awesome. Okay. And so user utility is given by aggregation. We're noticing that model creators are motivated by win rate, so basically how often their output is selected. This is motivated by what's used in practice. And just one thing I want to highlight is I've said that model creators are motivated by win rate. User utility is given by aggregation. You might think, are these related? Are these the same thing? A spoiler alert for the end of the talk is that these are sort of lead to attention, and we're going to propose a better mechanism to better align these. So that's the second half. There's a lot of related work in this space. I would say also sort of work on multi-agent systems, voting, human-algorithm collaboration more generally, a lot of work in mechanism design and leaderboards. There's a lot of that work being talked about this week, which I'm very excited about. It's been great. I would say one difference from a lot of this work that we're focusing on is specifically focusing on this imperfect aggregation. We're also specifically focusing on incentivizing firms, and these sort of actions of model creation and model replacement are more specific to different types of firm actions. So this is the outline. We already talked about the model. We're going to spend the first half talking about user welfare, so model creation and model replacement, what is good for users. The second half will be incentives, so how can we incentivize model creators to take different actions. If we have time, we'll talk some about experiments we did. Cool, so talking about user welfare. So this is the first question, what set of models is best for user welfare? And here we're going to focus specifically, we're going to start talking about creating new models. So this is exactly this diagram I had before. We have one model, now we have two models. And then replacing models. Okay, so the high-level story for all of this section is going to be basically this even sort of satisfying user utility is surprisingly complex. So there are cases where adding or improving a model could strictly harm users, could lead to lower user welfare. And we're going to describe exactly when this happens. So this is going to be relevant for the second half of the talk. So starting talking about market entry, so when is it helpful to add another model to the market? We'll start out with our two limiting cases. So one is random aggregation and one is perfect aggregation. And with perfect aggregation, if you can always find the best model from a large set of models, adding a new model to the market is always going to be helpful. You can just always find it, or you have sort of free disposal. And with random aggregation, adding a new model is only helpful. It's helpful if and only if it has higher accuracy than the average market. So basically, it's only useful for somebody to create a brand new model if it's like more powerful on average than the existing marketplace. With our aggregation, this sort of breaks, these two extremes break down. So we show that adding a new model sometimes helps, even if this new model is weaker than the average marketplace. So I'll talk through a specific example. I've created a set of, again, a very simple market with 3 different models. They're decreasing in sort of overall value or how powerful they are. And we're looking at user utility for different subsets of these models. So this is basically the utility for one model by itself, the most powerful model, then the sort of most 2 powerful models, and then finally all of them. And the user utility with beta noise parameter equals 1, in this case, increases. So even though you're adding in worse and worse models, because the user is sort of low enough noise, their utility is sort of systematically increasing. And what's happening here is that this model is like, sure, it's less powerful on average, but I've created it so that it's sort of patching a hole in the market. It's satisfying a need that doesn't currently exist if you only have these 2 markets, these 2 models. However, this is very temperature dependent. And if you have a higher temperature, you see the reverse effect. So adding in worse models sort of recovers this random aggregation limit where you're making things worse. So what's the high-level takeaway from this? If you assume that users are better than random, there are cases where it may be helpful for the market to sort of incentivize or have models enter the market, even if they're sort of systematically worse on average than existing markets. So there's a role for benefits to specialization when users are savvy enough. That's the high-level takeaway from this part. Now I'm going to talk about model replacement. And the story here is slightly more subtle, so I'll go through it in slightly more detail. Yes?
How did the insights in the previous slide depend on the exact utilities rather than just a ranking of the quality of the models?
Great question. So I can repeat the question. So how does this result depend on the user utility rather than the ranking? So user utility is given by the probability to pick the model and the value of it. So basically what we're assuming is suppose that the ranks are the same. So suppose that you have a responsive value 10, 3, and 2. User utility is very different from if it's 10, 9, and 8. Does that make sense? The values effect, which is sort of like if you're getting a coding answer, you don't care, maybe if it's better than what you could have gotten, you care like how good is the coding answer. Does that answer your question?
Yeah, so the choice model depends on the utilities.
Yes, and user utility depends on the utilities. Yeah, great question. Yes, we can.
So should I think of are we taking a average over the tasks when thinking about whether it helps adding a model or not? Or what exactly does it mean that the model, this hurts versus
Great
helps?
question. I should have said that more specifically. We are assuming you're taking an average or sum over tasks. If some tasks are, we consider generalizations where some tasks are more important than others, would be very cool. I don't think it would substantially change our results. But that would be a very interesting generalization. Okay, and the kernel blotto literature does do a lot of that work, if you're familiar.
Yes, thank you.
Yeah.
So for this finding that adding a new model sometimes helps even if the model is weaker, is this holding in this example where for task 1, Claude is clearly at least superior with respect to that task? Is it a condition that there has to be one task where
it's better?
Okay.
Exactly, yes. And that's actually, yeah, so if your model is worse than on every single task, it's not helpful. That's a thing that we actually cited from one of my previous papers, but yeah, so great question.
Thank you.
Other questions so far? Awesome. Okay, so now we're getting into model replacements. So toy example here, we have a world where there are exactly 2 models, and I'm switching it to a second world where there's, again, 2 models, but I've just made one of them systematically better on every task. So we went from 1 to 2 here, and from 2 to 3 on the second task. And we're curious, like, what happens to user utility? Again, it's helpful to think of our two limiting cases of perfect aggregation and random aggregation. And for both of these two limiting cases, if you strictly improve an existing model, you only help user utility. So it only stays constant or it increases. This turns out to not be the case if you had imperfect aggregation. So there are settings where strict improvement of models can actually like strictly hurt user utility. So I'm going to fill in numbers on this, and I'll show what's happening. So we have Bradley-Terry aggregation, and just with these values here, you can see, you can just work it out for yourself if you're interested. This systematically reduces user utility on both tasks and also on average. So what's happening? Why is this going on? For intuition, as you increase the value of each of these models, it increases the value, which is good, but it also increases the probability that that is picked, which could steal probability mass from better models. So this can net out to being worse. So just to show this in a graph, here's what's happening. You've got a value of a set with two items, v1 and v2, as a function of the value of one of the items, v2. And this is what this plot looks like. So as the value of this item increases, the value of the set decreases and then increases once it gets sufficiently high. And we're going to call this region where it's decreasing, in red here, this is the non-monotone region. So this is a region when the value of one of the items is increasing and the value of the set is decreasing. And this red region is generally considered bad. So one question you might think about, like, well, you picked Bradley-Terry. Is this just a function of Bradley-Terry? For a while, Manish and I were very angsty. We were worried we picked the one model that was bad. This turns out to not be the case. This is true of a much broader set of models. So two definitions I'm going to throw up here. One is a monotone function. So this is our definition. A function is monotone if for any set of values you give me, improving the values of it only increases user utility. So another way of saying this is it's monotone if there does not exist anywhere a non-monotone region. So there's no red region. A second definition is a function is separable if the probability of selection is proportional to some function of value. And as you might expect from the way I've stated this, these two end up being in tension with each other. So any separable choice function cannot always be monotone. So it cannot be monotone. And Bradley-Terry is separable, but there's a much wider range of functions that do satisfy this. There does exist a non-separable monotone aggregation function. It's in the full paper. It basically works based on the gap in values rather than the absolute value itself. So it does exist. But sort of it's an open question. I don't think you can necessarily guarantee the consumer is going to behave according to this exact function. So I do think this non-monotonicity is a real problem in practice. The other thing that you can guarantee, the good scenario, is if the user is sufficiently noisy, then you can get away from this. So specifically what happens is so long as if you give me some set of values that exist in the world, I can return to you a noise level, so a beta level, that's sufficiently high such that for those set of values, and for that noise level, you're not in a non-monotone region. So it's sort of an interesting result, where if the user is sort of too good, then you could end up in this non-monotone region. But if they're noisy, then at least you don't have to worry about this. Yes?
Is there an intuition why this doesn't work in the other direction? That if they become sufficiently unnoisy, that is also good?
It does. So in the limit of them being perfect, then this is good. I guess so there's the other extreme. So if you're either sufficiently accurate or sufficiently noisy, you're fine. If you're medium, then you could be in trouble. Great question. Other questions on this? Awesome. Oh, and here's a nice animation showing this happening. So you're increasing or decreasing temperature. And you can see the non-monotone region shrinks and then vanishes with sufficiently high temperature. Cool, so that's the first half of the talk. We were talking about user welfare. Now we're going to get into incentives. And we're going to talk about how do we create incentives to incentivize model creators to create better models. So second question here. And the sort of main model, agents want to maximize win rate. So they're trying to sort of maximize how well their model is picked or how often their model is picked. Users want maximum value, so some value over the set of models. When are these in tension and how can we create better mechanisms? Again, these are the two model creator actions we're going to be talking about. One challenge is that this aggregation function is non-convex, which we're going to mostly sweep under the rug, but did make some of the analysis more gross. Happy to talk about that later. And high-level results for this section, we're going to basically show that win rate is going to incentivize model producers to homogenize. So create models that have similar strengths and weaknesses, and this is bad for user utility. We're going to propose a new mechanism that incentivizes specialization and then show that this is generally better for user utility. So that's the high-level story for the next n minutes. So one question is, I'll talk about when can we design better mechanisms. To take Annie's question earlier, win rate doesn't give you enough information. So you're not going to be able to do this with win rate by itself. Instead, we're going to need a little more information. And that's going to be something we're going to call weighted win rate. So in this mechanism, the humans say the value of the item, not just which is better. And they're incentivized by the value times the probability the thing is picked. So you should think of this as basically saying, rather than saying you've got 3 models, which of them is better, you're going to say this one's better, and it's a value 6 answer, it's a value 2 answer. And we're going to show overall that weighted win rate ends up improving user incentives. Cool. So if we're going to start out with model creation. So in this setting, we have models that arrive sequentially. Each of them has some total value they can allocate, so they can be small, they can be large, or more or less powerful. And each best responds according to the mechanism that we've created. So it could be for user welfare, it could be win rate, or it could be our weighted win rate. And we're curious about 2 things. One is, what does each model do? So what action do they take? And then how does this impact user welfare? Yeah, so this is exactly what's happening. Cool, so first, welfare. What would you do if you were just trying to maximize user welfare? What you do is you just put all of your value on one task, and we show how to pick this task in the full paper, and you'd abstain on other tasks, so you'd give no response at all. This should be relatively intuitive. Opposite extreme, if you have win rate, so if total value is high enough, so basically if you're a powerful enough model, your incentive is to equalize win rate across tasks. So you can see they're doing here is they have sort of winning by exactly 1 on both tasks. So they're putting less value here and more value here because doing so equalizes their win rate across tasks. So what would you do with weighted win rate? What you'd end up doing is placing all value on a single task and value 0 elsewhere. So this is notably different from abstaining. Returning something of value 0 basically means returning garbage. Abstaining means returning nothing. So there is a difference between both of these. The next question, so this is what models do. The next thing is like, how does this impact user utility? And it looks exactly like these red lines here. So welfare is always better than weighted win rate. This is strict because of the 0 abstain thing. And weighted win rate is, as you would hope, better than win rate. Yes?
Sorry, can you say again what weighted win rate is?
It's value times probability of being selected. So win rate, if you have like, say, 3 models and your win rate is 60%, weighted win rate is 60% times the value you have. Does that make sense?
I can't get that from the definition.
Oh, that's the action. The definition is back here. I went over it a little bit quickly.
Oh, I see.
Does that make sense?
Yeah.
Awesome, thanks. I think I saw another question over there.
Yeah, I might have missed this, but what's the relationship between the value associated with the model on a particular task and the win rate?
Great question. So we're assuming it's generated by like Bradley-Terry Platchett-Luce. So basically, as sort of semi-standard assumption, so it's the value generates how often it's picked. And we're just proposing to change the mechanism from win rate to weighted win rate. Does that answer your question?
Yeah, so does that then introduce another temperature parameter for kind of the peakiness of the win rate itself?
We're assuming, so great question, I should have said this more clearly. We're assuming that the temperature just exists in the world. So people just have some degree of how accurate they are. When I give results varying temperature, that's because I don't know the exact temperature of the world. So I'm trying to give results that are true no matter how accurate people are. Does that answer your question?
Yeah. Makes sense.
Cool. Thank you. Great. So this is the result for model creation. Now we're going to get to results on model replacement. So with these other type of firm action that's more close to fine-tuning, what happens in this case? OK, so in this case, we're going to slightly change the setting. We're going to say there are models that already exist. Here we're focusing on settings where there are exactly 2 models in the market. And each of them picks a task to instantaneously improve on. So you pick one task to sort of improve on and get better at locally. So what does this look like here? This is a setting where they've picked different tasks. So this one picked task 1, this one picked task 2. This generalizes to arbitrarily many tasks. I'm just showing 2 for simplicity. So they're picking 2 tasks here. Here they're picking the same task. And we're curious about A, what actions do they take? And then B, how does this impact users? So first thing, welfare. What would you do for welfare? We showed that in this setting, it's always best for welfare if the firms pick different tasks. This just kind of makes sense. You're sort of getting better in different directions. If you're acting on win rate, we show that actually you're always incentivized to pick the same task. So you're always incentivized to sort of duke it out. What basically ends up happening is that you pick the task where it's sort of most in contention, and that's where it's sort of best or sort of most efficient for you to improve on. And this ends up, as you might expect, it will show it's worse for consumer utility. So what happens with our model with weighted win rate? You pick different tasks so long as you start out sufficiently specialized. So if you're sufficiently close, you might end up picking the same task, but so long as the market is already sufficiently differentiated, you're going to pick different tasks. Next question is, how does this impact user utility? So this is what they'll do. Now we're curious about, is this better for users? And the answer looks like this. So welfare is better than weighted win rate. However, we don't have the same result that we had previously. It is not the case that weighted win rate, our mechanism, is guaranteed to be better than win rate. I'm going to talk through when this fails. So in particular, we show that weighted win rate can lead to worse welfare than win rate, but only in one particular situation. And that's a situation when one firm is in the non-monotonic regime on both tasks. So you remember this diagram before? We had this red diagram here that's bad region. The only scenario where weighted win rate is worse is when you look at both tasks and one of the models is in the non-monotonic regime on both of them. So that's what's happening here if you set the values appropriately. This first model is worse than this second model on both tasks. And no matter what task it picks, it's always going to make things worse for the consumer. So what I would argue, you're in a sort of very unique situation where one model is sort of out of luck, because any task it picks to improve on, it's going to harm the consumer. And what I would argue here is you need a different type of action. You need a mechanism that can incentivize abstention. What you really want in this setting is you want to incentivize the firm to just not improve, not do anything at all, because anything it does is going to hurt the consumer. And that's, I think, one direction I'll talk about later that I think would be super interesting in future work. Yes?
So just to clarify,
in your theory, do you consider task distribution?
What do you mean by that?
Like how much people ask for a particular task?
We do not. I think that would be a cool extension. I don't think that would substantially change our results, but I think that would be a cool direction.
I see. So
Yeah.
I was thinking about it because like people also want to, like model developers, they want to create models which will serve the highest frequency task, right?
Yeah, and so that would be, there's this like very interesting kernel blotto to like contest literature that looks at some of this, where like you're sort of picking over like the biggest market or the sort of most in contention battlefields. That would be an interesting area to look at. I think that it wouldn't change the impossibility results here. You'd still have similar things. It's just the case that you might change sort of how you choose to allocate if certain tasks bring higher reward. Does that make sense? Yeah, great question. Yes.
So like thinking about like model creation, I initially thought that, Anthropic is creating another model. So in that sense, what I want is not even win rate, because I want the sum of my win rate to be higher, right? Like I am the same entity. Like, and I was actually wondering now that once you talked about abstention, I was wondering if somehow like creating different copies of Claude where each copy absentiates on different tasks is somehow like getting, I don't know, is there a way to like sort of like think about those things in this formulation?
Great question. So I'm getting maybe two questions. One is I'm assuming in this model that all of the firms are competing against each other. In reality, that's not the case. Great question. We don't model that. That would be very interesting. I would also suspect that it would require, it would sort of require colluding with the past, if that makes sense, where like I've released models in the past and then I sort of am okay stealing win rate from other models but not mine. So I think it's a little complicated to think about how to model, but I think it'd be very cool. And the other question is like, could you have multiple copies of Claude that sort of abstain on different types of tasks? That could be better for users if that's clear to users. So if they know like, this is the version of Claude that's good at coding, this is the version that's good at like whatever. I think that I would assume, sort of maybe to previous questions, that you might have some sort of aggregation if you're doing that, and that would just lead to like a more powerful model overall. Does that answer your question?
So yeah, thank you.
Awesome, thank you. Cool. So this is the end of theory. I think I have 10 minutes left, so I do have time for experiments, which I'm happy about. Cool. So in this set of experiments, what we did is we looked at a real market of models. So what we're curious about is all the things I've said so far is like, assume there exists some hypothetical model of markets. What we're curious about is like, what happens when we look at a real model of markets? So we used MTBench 101. And basically how you should read this is that there's a bunch of different models, and they have different values of tasks on different values on different tasks. So there are 13 different types of tasks, and some of them are better or worse at these different tasks. Yeah.
Maybe this is a good point to ask this question that I was wondering about
Yeah.
for a while. Maybe this is a good point to ask this question that I was wondering about for a while. How much of this is about models?
Yeah.
Like, it seems like you could replace the word models with, hatchbacks, where there are like a few different dimensions that are important for every hatchback. And replicate like everything exactly.
Great question. So there are two things that make this more specific to models. One of them is the firm creator actions. We assume they're sort of more motivated by things that we think are more natural for model creators to act. The other thing that's more specific to models is basically the fact that we can intervene in this way. So if you're creating hatchbacks, for example, it's not usually as easy to say we're just going to go in and change the incentives for firms without sort of also changing the ways that consumers experience like utility. So I think that's one
I see. So the fact that you control that it's a centralized market is the sort of
I think that's
the
part of it.
differentiating factors.
Yeah.
That
But I think sort of to the slides at the beginning, there's a lot of closely related work, and I would expect there's like definitely close connections to other areas. But I think those are the two things that are
right,
sort
like
of closest.
this point about non-monotonicity of softmax. This is a thing that shows up elsewhere.
Yeah, no, totally. Yeah. So definitely,
Thanks.
I would say that's something that I think is generally much more broadly applicable. But I think, so that's the point. So it's largely motivated by models, but I think would also have applicability to other settings.
All right, thanks.
Cool. Other questions? Yes.
Thanks. I had a question maybe a little bit, you don't have to go back to this slide, but sort of on the theory when you were talking about the instantaneous changes to models, like does that assume some amount of coordination whereby they would pick the same task, or is that like a equilibrium statement? Like how should I think about the firms each individually acting, but then like is it a statement that like there exists a task that is the best task for everyone independently to improve on and that task is the same? Or is it that like the global best thing to do if they could all talk to each other would be to improve on the same task?
So for the welfare, great question. The welfare thing is if you can globally coordinate, this is what you would do. And also if you were just myopically acting and you couldn't coordinate, the win rate, we are assuming that they're myopic. And that's kind of makes sense because you can't tell if another firm's going to sort of fine tune at that particular instant in time. We did think about some generalizations like Nash stability and things, which I think would be, and I think most of the results would generalize that setting. Does that answer your question?
Yeah. My follow-up was going to be, but it sounds like it's not relevant. It was going to be if you thought about like the dynamics of, like how the dynamics would actually go as opposed to like what the global optimal best.
We do. I can show you some pretty big figures afterwards. We didn't end up including them, but we did look at that setting.
Cool.
Yeah, great question. Any other questions? Cool. So now I'm going to talk about what happens in this particular data set or this particular benchmark. And so here, this is just the entire talk, and I'm just going to flash in red what part is relevant as we're going through, just so it's a flashback to previous things. So first, user welfare model creation. Our high-level result here was that adding a new model sometimes helps, even if that model is weaker than the current market, and that this is temperature dependent. So what does this look like in this particular setting? We basically vary temperature, and we look at which set of models is best for user welfare. And I'm only showing ones that are ever best. And you can just basically see, this is as you would probably expect. As you change the temperature, you want a smaller and smaller set of models, until if the user is sufficiently random, you just want to pick the best model in isolation. But there are regions where you sort of strictly benefit from aggregating across multiple models. Second thing, model replacement. So the two results here were that strict improvements of the model can actually end up hurting user utility. However, you get away from this if temperature is sufficiently small or sufficiently high. So you have these two extremes when things are good. And this is what this plot looks like here. Again, the x-axis is temperature, and the y-axis is the fraction of models that are in a non-monotonic regime. And this is a function of temperature. And you can see, like, at temperature equals 0, this would go all the way down to 0. At temperature sufficiently high, this goes down to 0 again. And you've got this sort of region in the middle where you could be a large number of models are in a non-monotonic regime. And this is like a surprisingly high fraction, like this goes up to 80%, which is like pretty non-trivial. So it depends on where you think you are, but it's likely a non-trivial fraction of models. The next thing we looked at was incentives. So this is model creation. This one is a little more involved. They go a little more slowly. So we said that win rate incentivizes homogenization, and that weighted win rate incentivizes greater specialization, and that weighted win rate is better for consumer utility. So for this example, what we did is we looked at a subset of the models. So we picked a subset of models, and we looked at what the different types of incentives would incentivize for a new creation of a brand new model. So how would these different incentives lead to different outcomes? So for this subset of models, the x-axis here are different tasks. And you can see like for the sort of initial market, there are some tasks that are underserved, like nobody's really good at this particular task. There are some tasks that are like pretty well served, so value goes up to 10. And first thing we're curious about is like, what would you be incentivized to do if you sort of showed up, brand new model you can create, and you're optimizing for win rate? So for win rate, you'd be incentivized to equalize win rate on tasks, and the added value you'd bring to the market is this shaded red region. So you can see that here you're sort of like winning by similar amounts in all the tasks, and this means that you sort of improve here a little bit, but sort of there's still a big gap of unmet need in this space. So this is what would happen with sort of status quo win rate incentives. What happens if you, yes?
Is the person coming into the market here like super strong?
Yeah,
Okay.
so this is why, yeah, so they're super strong. I think they have average value of like 8.5 or something, if I'm remembering correctly, but that's what's necessary for this win rate. Yeah, does that answer your question? Great, okay. What would happen if you're coming in and optimizing for weighted win rate? It would look like the blue region here. And just for a visual note, purple is mix of red and blue. So basically what you would do if you're doing weighted win rate is you sort of max out almost all of the tasks, and you'd abstain or not give any response or value 0 on one task that's sort of best served by the market already. You'd say, okay, they've already got this covered, I'm just gonna focus my efforts elsewhere. And just visually looking at this, there's a lot more blue region than there is red region. And this is just basically showing user utility is better or sort of improved more by weighted win rate than if you had win rate. Questions on this currently? Awesome. So the last part we got to was model replacement. And here we said that weighted win rate could lead to worse welfare than win rate, but only when you're in this non-monotonic regime. And so the thing we looked at here was like, okay, how often does this happen? How often is it the case empirically that weighted win rate ends up leading to worse incentives than win rate? And happily, the answer turns out to be not that often. So again, the x-axis is temperature, so we're varying temperature. And the y-axis is the gap. So basically, the gap in user utility for weighted win rate minus win rate. If it's above 0, then it's better. If it's below 0, it's worse. And as I've positioned the axes, you can maybe guess the answer, which is that empirically in this data set, it's always better. So this is not importantly an if and only if condition. We actually think so it's quite rare that weighted win rate is worse. And in most empirical settings, weighted win rate is going to be at least as good. So this is the high-level things I talked about. I'm going to briefly talk about future directions and then wrap up. So I think there are a lot of really interesting directions. One of them that I think is interesting is incentivizing abstention. How can you tweak this mechanism to incentivize firms to abstain or not improve their model when it's better for consumers? But you obviously don't want to do it too much. If everybody abstains, that's like quite bad. So there's some coordination failure. I think another interesting thing would be sharper constraints on bandwidth. So for example, it might be the case that the user is budgeted or there's some sort of cost to acquiring new models. That would substantially, if that's sort of strong enough, that might change the types of user utility. There's also a high-level connection with collusion, right? What I'm basically saying is that firms are incentivized to specialize. At a high level, you might worry, like, is that collusive? Like, when is this good? When is this bad? I think one thing you could also get at is, like, I'm talking about values. Acquiring these values is tricky. It might be imperfect. How does weighted win rate degrade when we have sort of imperfect values or estimates of values? And the last thing I'm interested in is like user studies of human choice, right? Like Bradley Terry is very commonly used. It's like a well-respected model. Is this how people actually behave when they're given multiple responses from LLMs? I don't know. I'd be very interested to find out. That is my talk. Thank you guys so much.
about what happens if you have a heterogeneity in beta? You could have heterogeneity in preferences, but also in temperature. The market dynamics, because the regimes you pointed out might all coexist at the same time.
That's a great question. We haven't looked at that specifically. Well, we like, assumed that users are the same because that was sort of the strongest setting to say that you do want heterogeneity. I think varying user preferences would be super interesting. We hadn't thought about varying temperature, but I think that'd also be super interesting. Like some people are better than others. I think the results would carry, but I think that'd be a cool area to look at.
Preferences you're sort of already varying because you're varying the tasks.
We're assuming that everybody cares about all the tasks. Does that make sense?
Yeah, but
you could say people. Yeah.
But like the beta varying them at the same time as you're varying.
That would be different. That would be cool. Awesome. Other questions?
I had a similar question about
Great.
if values were assigned to different individuals differently, if you thought about it.
Yeah. Cool. Awesome. Thank you guys so much.
Great. Okay, so now we have a break until 3 or so. Theoretically, there's a tea time at 3, which is when UIUC will start the next talk, but hopefully they will